Now we want to take a look at this conversion between work and heat a little more closely. Remember that work and heat are the two ways that we can exchange energy between a system and its surroundings. So let's take a look at this scenario here. Let's say that we want to design a machine that will take work from the surroundings and provide heat to the surroundings. Now notice here, this is a similar schematic to before. I only have one thermal reservoir here because I'm only exchanging heat with one reservoir right now. So a machine that consumes work and delivers heat. Is this possible? That's what we want to ask ourselves. Well, it turns out this is very, very possible. In fact, it's very easy to do this. Just take your hand and put it on the desk and rub the desk back and forth for a minute. Okay? So you are doing work on that desk because you're exerting a force through a distance. So work is going into that process, into that cycle you're doing. Well, what is the effect of that work? Well, you're producing heat. Your hand's getting a little bit warmer. The desk is getting a little bit warmer. All of the work that you are doing is being converted to heat. 100% of it is being converted into heat. So this process, as we've shown it here, is really quite easy to achieve. Here's another way that we could do the same thing. Let's say we had a container with some fluid in it. It could be a gas, could be liquid, doesn't really matter. We have a paddle wheel inside there, so a little propeller or paddle wheel or something, and we turn that. So we're doing work on this substance. So there's a torque acting through an angular displacement. We're doing work on the substance. And we allow heat to transfer out of this thing so it's not an insulated container. And we let this thing reach steady state so that the temperature inside here is constant. So what's happening here is 100% of the work is being converted into heat. And this thing can run continuously, so it's operating in a cycle. There's no net change of the system because the temperature is constant. So 100% of the work that comes into this thing is converted into heat, and there's no change in the state of the system. So this is another illustration of converting work into heat with 100% efficiency, essentially. The conclusion we come to here is that this is possible. We can think of many situations where this is happening. Work converted into heat. So now what we want to look at is the opposite case to this. So we want to ask ourselves now, what about the opposite situation? And notice the only thing that's changed in this diagram is the direction of these two arrows. So we now have a cycle or a machine that is accepting heat from the surroundings and using that heat to produce work. Can we do that? Well, of course, there are a lot of machines that do that, and we're going to be talking about several of them as we go forward, but we want to know, is it possible to achieve this scenario? And notice this is operating in a cycle, so if this Q is 100 kilojoules, then this work has to be 100 kilojoules. We were successful in the opposite direction in converting 100% of our work to heat. Now that we've switched these arrows, can we convert all of this heat into work? In other words, is this scenario possible? Because this is operating in a cycle, so these two things have to be equal. Well, we're going to try to do that. Now, we're not going to try every possible way, of course, but we're going to illustrate a difficulty with this particular energy conversion by trying to do it in the context of a piston cylinder device like we're familiar working with here. We have an ideal gas, and we're going to follow the progress of this on property diagram here as well. So the first process that we're going to look at here is going to go from state point 1 to state point 2. We're going to add heat to this substance, to this ideal gas, and we're going to also allow it to expand during that heat addition so that work is delivered to the surroundings. Now we're going to let it expand in such a way that the temperature of this gas remains constant. So the temperature remains constant. So we're adding heat, temperature remains constant, and it's delivering work to the surroundings. So on a PV diagram, we're following a line of constant temperature. So that's the process from 1 to 2. Now, because the temperature is constant, the state of the system has not changed. In other words, the energy stored in the system is the same because that's a function of temperature. So Q minus W is delta U. The delta U is 0, so during this process, Q must equal W. We set out to convert heat into work. Well, we have done that. If this is 100 kilojoules, then this is 100 kilojoules. So we've converted heat into work with 100% efficiency. So things are looking very good. So 100% of the heat supplied has been converted into work. So things are looking good. The problem, however, is that this cannot continue on indefinitely. We can't just simply let that gas continue to expand because there's a limit to how large we could make this thing. So we need to get the system back to state 1 so that we can do this over again, so that the thing can operate in a cycle and continuously convert heat into work. So we're going to investigate how to get back to the original state. So our original process is along a line of constant temperature. So one option to get back to state 1 would be to just return along the same path. So go back along the same path. So there we've been successful in getting back to point 1, so we've operated in a cycle. The issue with that, though, is this would give no net work. So the work delivered to the surroundings during the expansion would be exactly the same as the work that the surroundings would have to give back to our system during the recompression. And so there'd be no net work available in the surroundings to do anything. So yes, we've reversed the process, but with no net work production. So that doesn't work. So remember, work is the area underneath this curve on the PV diagram. So we need to return from 2 to 1 along a path that has less work. In other words, lies below this line somehow. So that's the key to getting back to point 1 and having some net work production. So we must return along a lower path of some sort. So remember that this means we need to recompress at a lower temperature. So remember, this is a line of constant temperature. Anything above that line is hotter, anything below that line is colder. So we need to get from 2 to 1 along some path that is colder than our original expansion. That's the key to producing a cycle that will continuously convert heat into work. So let's see how we can do that. So here's our original process, 1 to 2. What we're going to do here to get the temperature lower is we're going to actually continue to expand this gas. So we're going to let the piston continue to move up as we go from 2 to 3, our next process in this cycle. Only now we're going to not allow any heat transfer to happen. So the difference here between our first process and this one is this is now an adiabatic process. No heat transfer. Well, if we continue to expand this gas and don't allow any heat transfer, then the temperature is going to decrease. So this is an adiabatic expansion to a new temperature, Tc. So work will still be developed during this process, so positive work still. And on the PV diagram, the temperature will decrease. So notice this is a steeper line. That's a line of constant temperature, but now with further expansion, the temperature drops down. So this is a steeper line. So temperature point 3 is this new temperature Tc, the cold temperature. So that's fine. This is just the technique that we've used in this particular cycle to get down to a lower temperature. Now we need to turn around and start reducing our volume. Remember, our goal is to get back to this spot along a path that is below this one. So we've managed to get down to a lower temperature. Now we need to turn around and get back there. So in this particular cycle, the way we do that, so now we're talking about the next process from 3 to 4, is we remove the insulation again. So now we have no insulation and we start to recompress. So we now need to do work on our gas because we're going to be moving from right to left. The volume is going to reduce. The surroundings are doing work on our system. And we're going to recompress this gas just part way so far. And we're going to do it in such a way that the temperature remains constant. So remember, our original process here was constant temperature. And this third process from 3 to 4 is also constant temperature. Only it's occurring at a lower temperature. So there will be some heat that will need to be removed during this process in order to keep that temperature constant. So work being done on the system, heat being removed from the system, and the temperature remaining constant. So on the PV diagram, we're going to be moving from right to left along a line of constant temperature. And so another isotherm, 1 to 2 is an isotherm, 3 to 4 is an isotherm, and we recompress partially. Notice 4 is not immediately underneath 1, the volume is still larger. Now remember, our goal here is to get back to point 1. Well, we're not going to get to point 1 if we continue along this isotherm. We need to do something to get back up to this point. So in this particular cycle, what we do is we continue to compress it, but we stop the heat transfer. We insulate it again, so we get from 4 to 1 adiabatically. So that's our next step. So notice we're insulated again. We're going from 4 back to 1. We're doing work on the gas still. So work negative, work input to the gas. Q is equal to 0 during this process. So this is an adiabatic compression. And that takes us from 4. We're compressing adiabatically, so the temperature will increase as the volume decreases, and we go back to 1. So notice we have now completed a cycle. So now those 4 processes acting in that order form a cycle. So now we have a machine that can run continuously. It could just repeat this over and over again, and it's continuously converting heat into work. So we have been successful now in forming a cycle out of this by using these other processes to get back to point 1 along a path that is underneath our original process. So this just shows the PV diagram a little bit larger. So we'll just review what these 4 processes are. The first process was constant temperature heat addition. Second process, an adiabatic expansion. Third process, constant temperature heat rejection. And the fourth process, adiabatic compression. So those 4 processes form a cycle. Now what we want to do is go back and review this original schematic diagram and see if what we set out to achieve has been achieved. In other words, have we been able to devise a cycle here that receives heat from some high temperature reservoir and produces an equal amount of work? So let's think about these 4 processes again and think about what the heat transfer with the surroundings is during these 4 processes, so we can relate that to this. Well, remember that the process from 4 to 1, the last process, was adiabatic, and the process from 2 to 3 was adiabatic. So these 2 processes, there's no heat transfer with the surroundings at all, so we don't have to worry about those. The process from 1 to 2 is where our cycle is receiving heat from the surroundings. So the QH in this schematic is happening here as we go from 1 to 2. Heat is being supplied to our cycle from the surroundings, and that's what's happening from 1 to 2. However, we look at our cycle, we see that is not the only heat transfer that is happening. This schematic diagram shows that the only heat exchange between our cycle and the surroundings is this QH. But if we look at our processes, there's another heat transfer that is happening, this QC. During the process from 3 to 4, heat is being transferred out of our cycle, or we say heat is being rejected from the cycle to the surroundings, and the amount of heat is QC. So this schematic diagram that we started off with is incomplete, and instead we need to add another reservoir here to represent this heat rejected to a cold reservoir. So this is happening at a lower temperature than TH. We talked about why we needed to recompress at a lower temperature. So the original diagram was missing this part. So what we've learned here in going through this cycle, in trying to devise this cycle, is that heat has to be rejected. So the fact that heat has to be rejected to a cold reservoir is the same as saying in order to get from 2 back to 1, we have to go down to a lower temperature. And there's no way to get from 2 back to 1 without rejecting some heat out of our cycle into the surroundings. So this has to occur in order to convert heat into work. And what that means is that when we look at the overall energy balance here, if we have 100 units of energy coming in here, doesn't matter whether they're BTUs or kilojoules or joules, just 100 units of energy, it is impossible to produce 100 units of work because some of it has to go here. So the conclusion here is that it is not possible to convert all of this heat into work. Some of it has to go down here. So heat has been rejected to a low temperature reservoir, and the Kelvin-Planck statement of the second law says that this must occur. So we earlier talked about the Clausius statement of the second law. There is a second statement of the second law that is related directly to this scenario that says that has to happen. The only way to convert heat into work is by allowing some of the heat to escape to a low temperature reservoir. So now let's take a look at a formal statement of Kelvin-Planck. It states, it is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of work to its surroundings while receiving energy by heat transfer from a single reservoir. So if you'll notice, this is describing the scenario that we set out to do. We had a single reservoir and we were drawing heat from it and delivering work to the surroundings. So that is not possible.